What is the JVM, or the Java Virtual Machine? So in order to answer that, we first have to go explain what a compiler is. So you remember uh, the CPU in your computer implements one particular instruction set, right? So that is the programming language that the CPU implements itself. Uh, you can write in the early computers, people would just write their code using this instruction set. And those were we call assembly language programs. So the assembly language is basically almost just like the instruction set. It has a few little niceties, so it uses LDA instead of, say, the number 62 for the load accumulator function. So assembly languages turns the machine code, which is just numbers, and gives them nice little mnemonics like this one. But it doesn't do much more than that. It is still basically just the instruction set of the CPU. So people wrote, though, and still do write assembly language programs, but this is very low level. So if you want to do something as simple as, say, print hello world, you would have to say, okay, load the letter H, okay, put that letter over there so it gets displayed, okay, load the letter E, put it over there, load the letter L, put it over there, load the other letter L, put it over there, and so forth. So quickly people realized that was very tedious, and they thought, well, maybe we can come up with some higher level programming language. That we can then turn into this assembly language. So at first they did this by themselves. Let me write up here. So we call those higher level languages. And basically these are all the programming languages that you've heard of, like Java, C, C++ language. So one example would be the C programming language. And that C programming language then gets turned into assembly language. What they did was they wrote another program called the compiler. So the compiler is a program that takes as input a C program and outputs the assembly language or the machine code that then runs in the CPU. So and that's the way it worked for C and C++. These are compiled languages uh, that get fed to a compiler, which is just another program, and that program turns this program into an assembly language program. There's also interpreted an interpreters. An interpreter is very similar to a compiler. So a compiler takes C or C++ and turns it actually into a .o file. Um, And then this file has all the assembly language and that file runs. An interpreter takes in the language, say Perl, it's an interpreted language. The interpreter takes it in, reads the program, and as it's reading it, it turns it into assembly language and then reads it again, turns it into assembly language. So it never creates this compiled file. So this file here contains assembly language, and so the difference is a compiler. You do this step once, you get your assembly language file, and then you run this file any number of times. So you don't have to do this part. With an interpreted language, you take the file, you turn it into assembly code, and you run it, but you never create this file. So next time you run the same program, you're again going to have to turn the Perl file into assembly language. So thus compiled programming languages are faster because once you get the assembly language file, you don't have to redo that first step every time. You just do it once and you're done. Okay, so those are compilers and interpreters. What the Java people did is a little bit different. They built the Java virtual machine, which sits right about here, right? So the Java virtual machine takes as input what they call bytecodes and interprets them into the assembly language. And those bytecodes are really very similar, but not identical to the instruction set, right? So the idea is that the Java virtual machine is like a CPU. So a CPU implements an instruction set. The Java virtual machines implement these bytecode, this programming language, which is very, very similar to the instruction set that, say, the Intel CPU implement, but not exactly, right? So there's a few little differences. So because it is very similar, that means that it can do this part really fast because turning bytecodes into assembly language is really easy. So it can do that really fast. And the advantage is if you change your CPU, you can then just build another JVM. So say that JVM works for this CPU, you can build another JVM that works for this other CPU over here. And both of them take as input bytecodes. Therefore, Java can run in different computers. And the part over here that's missing, so is the part that takes your Java program, and we run that through the Java compiler, and this generates bytecodes, right? So when you're running Eclipse, when you hit the compile button, it takes your Java file that you wrote and runs the Java program, that's the Java compiler, and that creates the bytecodes. These go into your .class file, right? And your .class file contains bytecodes. Then when you run that, then the JVM runs, picks up those bytecodes and runs them and turns them into your local instruction set. So the JVM is a two-step process, or if you like, you create this .class file, and then that .class file is not a .o file, so it's not written specifically for your CPU, but is written in bytecodes, which is very similar to your CPU. So that means you still need this JVM virtual machine to interpret those and turn them into the language of your own CPU. So if you look, here's the Java file. Here is my workspace. I have a program here. I have the bin and the source folder. If I go into the source folder, you see my Java file. That is just a text file. It contains a little program. If I go back to the bin folder, because I already I compiled it. Sorry, cd bin. I have the class file, and you can try to look at it, but it's not going to work very well because it's binary. But these are the bytecodes that represent the program.